Hello, this is Chris Englert from the Naval Research Laboratory. I'd like to give you a brief introduction to MIGHTI, the wind and temperature instrument that is on the ICON satellite. Then I will hand off the mic to Brian Harding from the University of California, Berkeley, who will show you some of the first results. The ICON mission, of course, was designed to explore the space environment near Earth and to discover the sources of its remarkable variability. There are 4 instruments on board, one of which is MIGHTI, to measure the horizontal wind vector profiles and the lower thermospheric temperature. In order to do that, we use naturally occurring air glow emissions of oxygen, the oxygen red and green line, and the oxygen A band. There are actually 2 identical sensor units, MIGHTI A and MIGHTI B, that allow us to measure the wind vector profile, and I will show that in a few slides. Here's a picture of the satellite, fully integrated. The instruments are shown on top here. Now it is flying in orbit with the instruments on the bottom side of the satellite. The launch was on October 10th, 2019. It was a beautiful night launch with a Pegasus rocket, which brought the instruments together with the spacecraft into an almost perfect circular orbit. Now, how do we measure winds? We use spectrally isolated emission lines like the red and green line to measure the Doppler shift. And the way this works is that we use a Michelson interferometer to transform the signal into the Fourier transform of the signal, which is basically a fringe pattern, interference fringe pattern as shown on the right side here. Now a small Doppler shift of this emission line changes the spatial frequency of this fringe pattern by just a tiny little bit. So it's almost indistinguishable at low optical path differences, but at higher optical path differences, you can see a cumulative phase shift. And that is really what we're measuring. We're measuring the phase shift of this fringe pattern, which tells us about the wind. And there are a few pictures down here of integrated monolithic dash interferometers that are flying on ICON. The size of this is about the size of my fist when it's integrated in this holder. For the temperature, we use the fact that the shape of the oxygen A band is changing with temperature. So the spectral shape is changing according to this figure that is shown right here. And we just have a few filters that are about 2 nanometers wide on the band, and then 2 more on the sides to get the background contributions. And the relative signals of these filter channels give us the information about the temperature. Now the measurement geometry is depicted here. One MIGHTI line of sight is pointing 45 degrees from the velocity direction, typically to the northern hemisphere. And then MIGHTI B looks backward 135 degrees from the velocity direction of the satellite. And about 7 minutes or so apart, those 2 lines of sight sample the same area in the atmosphere, the same tangent point location. And each one of those measurements makes a determination of the wind speed in the direction of the line of sight, and the combination of those 2 give us the wind vector profile. Now this is what the raw data actually looks like. There are 2 exposures shown here, one MIGHTI A and one for MIGHTI B. On the left-hand side, you see the green line fringe patterns, and on the right, the red line fringe patterns. And on the bottom right here, you see an area that is used to measure the temperatures, and you can recognize the 3 channels on the band and then 2 channels on the edges here for the background signal. The MIGHTI A picture shown here is actually with calibration lamps on. There are 2 onboard calibration lamps which allow us to track and correct for the thermal drift of the interferometer. There are a few points I want to make here. All altitudes are sampled at the same time, so there's no scanning mirror that points the line of sight up and down. Every tangent altitude is measured by a different instrument, meaning that the signal goes through different parts of the optics and is detected by a different part of the detector, which means that cross-calibration of the altitudes is key to get the right inversion results. And lastly, to give you an idea of the magnitude of Doppler shift and fringe phase shift that we're looking at here, if you assume a Doppler shift equivalent to about 100 meters per second, that causes a phase shift of only about 1/400th of a fringe. So really small change. That's why we really have to be worried about understanding the instrument completely and correcting all little thermal effects, for example. And this is exactly what it was built for. Now, at this point, I'd like to give the mic to Brian Harding, who will show you some of the first results. Over to you, Brian.
Hello, everybody. This is Brian Harding from the Space Sciences Lab at UC Berkeley. Here I'm showing 1 day of MIGHTI zonal winds. That's the east-west component of the wind vector, from 90 kilometers up to 300 kilometers. This plot's organized by solar local time and shows about 15 orbits that compose a day. The green line winds have been stitched together here with the red line winds at about 180 kilometers. So above 180 kilometers is from the red line, below 180 kilometers is from the green line. You can watch as the spacecraft goes from midnight, which is here on the left, across the dawn terminator to the day side, which is here in the middle. And during the day side, we have full coverage from 90 to 300, whereas at night, the red line and green line emissions become narrower in altitude. So we don't get any usable signal between about 110 kilometers and 210 kilometers. The precession of the orbit is slow, of course, relative to an orbit. So when the spacecraft completes one orbit and comes back around to the same local time, it's at approximately the same latitude, almost exactly. That has an important implication here in that if the entire thermospheric wind structuring were due to migrating tides or other sun synchronous structures, each one of these orbits should look exactly the same. It should have the same pattern. But nevertheless, there's an incredibly rich variety of longitudinal variability that's exhibited here. You know, from one orbit to the next, there's significant structure that exhibits as either small scale patterns here, for example, where you can actually track a disturbance seeming to connect between the green line all the way up to the red line up to 300 kilometers. Or the other pattern of variability is these very strong winds organized in narrow shear layers, sometimes only several kilometers in altitude and reaching up to 150 meters per second. So with a single satellite, it's difficult to tell whether the structures you're seeing changing from one orbit to the next, or even along the orbit, are due to spatial variability or temporal variability. But one way to disambiguate that is to look at multiple days. So here I'm switching back and forth between February 2nd and February 3rd, 2 days, same data. And again, the precession is slow. So on consecutive days, you're sampling you're basically sampling the same locations on Earth. It's clear from these data that some of these shear layers, these localized, narrow, strong winds, seem to persist, where from one day to the next, so for at least 24 hours. Yet other structures vary significantly from day to day. They show up one day and the next day they're gone. So it's as if some of these structures are pinned to the Earth. This particularly strong layer here seems to be localized off the east coast of the United States, up here in the mid-latitudes. So these strong shear layers, of course, have been seen before, and particularly by chemical release trails. But these MIGHTI data show that they're ubiquitous. Even in daytime, even at low latitudes, and they're widespread. They exist over thousands of kilometers of horizontal distance, and they last for 24 hours. They're there the next day. So this kind of variability is really a key science target for ICON. In particular, how it will drive the variability in the dynamo electric fields and therefore variability in the ionospheric density. This is some work by Jonathan Makela comparing our MIGHTI winds to ground-based observations of the wind. So he compared 74 coincident observations between MIGHTI and this ground-based Fabry-Perot in Urbana, Illinois. Of course, there's very different viewing geometries involved here. The Fabry-Perot looking up measures some sort of altitude integral of some weighted average wind. But since MIGHTI is able to actually resolve the altitude profile, it can be used to predict what altitude weighted wind the Fabry-Perot should measure. And then you can compare that to the actual measurement. And that's this plot here on the bottom left. So each one of these dots is a coincidence or a near coincidence within a couple hundred kilometers of MIGHTI tangent point with the FPI 250 kilometer Pierce point. So there's really a remarkable agreement here given the differences in the viewing geometry. So that's very encouraging. The slope is near 1, which of course means that the variations seen by the FPI match the variations seen by the by MIGHTI. More exciting though is the fact that it validates the zero wind reference. All interferometers have this challenge of defining their zero reference. You know, what is the phase that corresponds to a Doppler shift of 0? The fact that the y-intercept is small as near 0 here means that the MIGHTI zero reference currently used for this data product matches the FPI zero reference, which was used by assuming that the long-term vertical wind averages to 0. So that's encouraging. This is just one example. He has many more, and I'll encourage you to go see his talk in the Concert 2 session on Wednesday. So just to wrap up, MIGHTI is not the first space-based wind sensor. It follows in the footsteps of previous successful observations by Hardy, Windy, and Tidy. It takes advantage of advances in detector technology as well as instrument development. But more excitingly, it has the advantage of no duty cycling. MIGHTI is able to simultaneously measure the Doppler shifts of the green line, the red line, and then use the O2A band channels to infer the temperature. And it can do this simultaneously. So although previously I just showed 2 days of zonal wind data, we of course have meridional wind data and temperature, and we have it nearly continuously for 6 months. These data are becoming publicly available starting the week of CDAR. But maybe the most exciting thing to me about this new data set of winds and temperatures is that it exists in concert with these other collaborative data sets. The FUV to give ion density and neutral composition, the EUV to give ion density during the day, and most exciting, the IVM to provide ion drift or electric fields to really get at the connection between the variability we see in the winds and how that drives the variability of the ionosphere. And that work is currently underway. If you're interested in using the MIGHTI data or any of the ICON data products, I'd encourage you to attend the ICON session of the data tutorial, where we'll be going in depth into each of the data products, the do's and the don'ts, and to help get you started. Thank you.